Hello everyone. Welcome to this session ARC312 Journey to Cell-Based Microservices Architecture on AWS for Hyperscale. My name is Anand and I'm a Senior Solutions Architect at AWS supporting digital native business customers. These are customers who take a cloud-first approach to IT and operate a hyperscale environment to support the growth in their business. And I'm joined together by my colleague from DoorDash, Jay Wallace.
Hi, everyone. My name is Jay. I'm an engineering manager for cloud infrastructure at DoorDash. I've been with the company for about 5 years, which is great because I've been able to see our architecture change over the course of those 5 years. This morning, both Anand and I are going to be walking you through today's session.
So let's take a quick look at the agenda. We'll be sharing with you the journey of DoorDash, a technology company with its fastest growing last mile delivery platform supporting local commerce. We'll begin with the early days of the monolith and how it has evolved into a microservices architecture and the adoption pattern. We'll look at what hyperscale means, challenges of running microservices at hyperscale, and how cell based architecture helps in addressing those challenges. We'll also take a quick look at how AWS helps in that design. We'll then turn our attention specifically to DoorDash Supercell project, where they have implemented this architecture, and then end the session with some key learnings and next steps. You are expected to have some familiarity with AWS networking services and then some of the compute and database options available on AWS. Both me and Jay will be interleaving our talk as Jay walks through the DoorDash's journey and I talk through the concepts of the architecture and the AWS service ecosystem. Let's start then by looking at the DoorDash's business model.
Awesome. Thanks, Anand. I'm sure many of you out there have probably heard or used DoorDash, but for those of you who may be less familiar, we're a tech company, and our main goal is to connect consumers with their favorite local businesses. And today we operate in 27 different countries. A little bit more about our business. We operate a three-sided marketplace that consists of our consumers, our merchants, and our dashers. We operate in various verticals, everything from food to groceries to home goods. And today we have around 25 million consumers, 550,000 merchants, and over a million dashers fulfilling delivery on the platform. And of course, none of this would be possible without the hard work of our 15,000 employees across the globe. I want to start this morning by providing a bit of DoorDash history and specifically looking at how our architecture's changed over time and what drove some of those decisions. 2013 is actually a really great starting place for this because this was the year that DoorDash was founded and shortly after our monolith was born. Um, as with most early stage startups, the focus early on is building and delivering. So Django was chosen for our monolith, as is what our founders knew, and it allowed the team to move quickly and provide a unified framework for both the front end and the back end. If we take a look at the pictured monolith, it's not too much like our own. Our monolith was a Django web app, and our main DB was Postgres. And this is basically a lot of monoliths. A monolith is typically a large system using a single code base, and it's deployed as a single unit or a single service. And it's usually just put behind a load balancer. And early on, there's a lot of advantages to this. One of the first advantages is around simplicity. Monoliths are simple to build, test, and deploy. They're easy to scale horizontally. And then there's lots of sharing between the various components. So you only basically have to do something once. So you could share components like, you can share across your components things like logging, pipelining, config management. And then, of course, lastly, performance is a really great advantage with regards to the monolith because you don't have to contend with any inter-service network latency because everything is an in-memory call between the various services that are part of your monolith. This, of course, doesn't come without its own drawbacks. Otherwise, we'd always be using monoliths. The first is tight coupling that affects the management or scalability and continuous deployment of the code base. So if you think about it, if you wanted to cut a new feature, you'd have to do a full deploy of the monolith to land that new feature. As the code base grows, it inevitably becomes more difficult for an engineer to understand and begin contributing. Adding new capabilities is super slow. And then lastly, although I kind of shared earlier that sharing is an advantage, it also poses as a disadvantage where if you have sharing of modules across your code base, you end up with a blast radius issue where if someone makes a change to a shared module, it may result in an undesirable consequence in an unrelated service, causing a failure. And for us, that was pretty much the state of the world up until 2014 when we had our first microservice. It was our logistics AI service. And I want to use the term microservice here very loosely as it wasn't part of any sort of grand re-architecture or anything like that. But it was rather because Scala was a better choice for CPU-intensive tasks than Python. And this actually isn't too uncommon. You might actually be seeing this as in your own journey right now. You might have a team that might be spinning off some new service or working on something independently, and they want to take advantage of a specific framework or technology that's just better suited for their needs. By 2017, we had begun spinning up various services outside our monolith, but really they lacked clear direction and intent. Our monolith had really begun to hit some serious limitations. For one, the team itself had grown significantly since the early days, meaning that we released software more often, and that since there weren't individual deployable units, it was super slow. Our pipelines began becoming painstakingly slow because we had unit tests that were stacking up, which resulted in either engineers opting out of some unit tests, which meant there was less guarantees in a given deployment, or accepting that deploying software was going to be slow. Plus, as I previously mentioned, for engineers to get started, there was a steep learning curve when it came to learning the monolith code base. Lastly, as I alluded to in the previous slide, there was no failure isolation, so updates in one place would often result in issues in another. Our next phase was in 2018 when our company went all in on microservices. During this phase, we continued to grow as a company and grow into various new verticals, and our order volume increased, our customers increased, our merchants increased. But the focus at this time was really to allow our engineers to work on components and services independently so they could be more agile. But at this point in time, the monolith itself was still at the middle of a lot of critical flows. We had a bunch of microservices that folks could work on independently in Kubernetes, but unfortunately, a lot of these microservices had this issue of strong dependencies, where the reliability actually became the product of the reliability of the strongly entangled services. This is actually called a distributed monolith, and it's an anti-pattern. In 2019, we refocused most of our efforts, and we took a much more thoughtful approach on how we were thinking about microservices. And there was this aggressive push to get everything out of MainDB and into domain-specific databases. We also created standards across the board. I think the most significant that would be worth calling out is that we pushed for the adoption of Kotlin across all of our services. To give you some context, in the early days, it wasn't too uncommon for a service to be written in Python or Go or Java. But adoption of these new standards allowed the team to invest heavily in authoring common libraries that solved common problems or shared issues that all of our services had, such as providing out-of-the-box request fallback techniques, load shedding, better observability through things like distributed tracing. And then overall, what really emerged was this multi-layer architecture consisting of multiple front ends, a BFF layer, which provided functionality to the front end by orchestrating interactions with the back end. We had our core functionality or back end layer, which is pretty much all of our microservices. We had platform services that were leveraged by those core services. You can think of this as something like identity is a good example of a platform service. And then the underlying infrastructure itself. So, things like databases, caches, queues, everything that was sort of managed by the infrastructure team. But I'll pass it to Anand to share a bit more about what microservices look like that he's maybe seen and what a typical adoption looks like for most.
Sure, Jay. And so, rightly mentioned here, right? Like microservices allows your application to be composed of loosely coupled small autonomous services that can be deployed and scaled independently, and it offers several advantages. So, first of all, to scale the application, you only need to scale certain components of the application and which optimizes resource usage. Now, these microservices are loosely coupled, so they are not interdependent on each other, and so can be individually tested. So this makes the application more adaptable to changes over time. They help break down these large confusing applications into smaller ones, which the teams can specialize in. So the development teams get productive more quickly. They can deploy these services independent of the other services. Each of the smaller services is easy to test, easy to debug. Now, this kind of architecture also gives these teams some technological freedom as they are not tied to the same language or technology stack that the original monolith started with. All of this translates into more agility for the teams. So, just as we saw in the DoorDash's journey here, one of the ways to migrate to a microservices architecture is a pattern invented by Martin Fowler called the Strangler pattern. And the main idea behind this pattern is you will start building new capabilities and systems around the current systems so both will coexist at the same time. And this allows your migration to the microservices to happen without impacting the application and the ongoing operations. So essentially refactor the application in two ways: add new capabilities as separate microservices and make the microservice call the monolith instead of the other way around, and then take some functionality out of your monolith and make it as a separate microservice. Now, one of the pattern to avoid here is building new capabilities on the monolith itself, as well as making the monolith application call your microservice, as that introduces additional code on the monolith instead of shrinking it. Another pattern to avoid is going too granular with your microservices approach, where you use technology and infrastructure for decomposition. Instead, use approaches like domain-driven design for service decomposition. Now, the technological freedom that we were talking about means you can run some of your services on Elastic Compute Cloud, EC2 for short, which provides virtual machines with variety of instance types to suit different types of workloads and run them behind Elastic load balancers. You can run some of your services as containers using Elastic Container Service, a fully managed service, which allows you to build, deploy, and scale containerized applications. Now, let's say if you have Kubernetes workloads, you can take advantage of Elastic Kubernetes Service, which manages the availability and scalability of the Kubernetes control plane. Now, let's say you have services which are more event driven. Use AWS Lambda, which provides a serverless event driven compute and provides ability for running any kind of application without having to provision or manage servers. Then for the choice of databases, you have choice of purpose-built databases, starting with Amazon RDS, the relational database service, supporting a variety of database engine types, and Amazon Aurora, which provides high availability and scalability with full MySQL and Postgres compatibility. If you are looking for NoSQL data stores, you have Amazon Dynamo DB, which is a fully managed service and serverless, which provides you that NoSQL data store. And for all other types of data, you have Amazon S3, which provides 11 nines of durability and high availability. Now, there are some messaging services on AWS as well, like Amazon SNS, Amazon SQS, Event Bridge, Kinesis data streams. All of these help you to build those loosely coupled architectures. And then you can expose your microservices as APIs using Amazon API Gateway, which is a fully managed service which allows your developers to publish and secure APIs. Now, this microservice architecture is definitely promising, right? But there are several challenges that you encounter along this path. First of all, identifying the right service boundary so that all these services operate in a loosely coupled and in an autonomous way is challenging in complex environments. In this system, with each service managing its data independently across data stores, the problem of data redundancy becomes real. Take, for example, data that might be stored for a particular transaction in one service. That same data might be stored in another service for reasons such as analytics, reporting, and so on. And the overall system would be in a consistent state only after all the services have performed their work. Now, what was an in memory call within your monolith becomes one that transits between processes on the network, bringing with it concerns about latency, performance delays. Additionally, if you don't have any monitoring tools and testing tools in place, things can quickly get escalated out of control. There are more services to monitor. Each service has its own set of logs, and makes it hard to find the source of the problem. So these interdependencies between services needs to be closely monitored, and any downtime of a service due to outages or upgrades can result in cascading downstream effects. Building, deploying, and running microservices at scale requires you also to have consistent CI/CD practices, and each service will have its own parameters based on which they scale. All of this adds to the operational complexity.
I can say that we at DoorDash definitely went through a lot of these when we were undergoing hyperscale. I think the most notable that's probably worth calling out is just the sheer increase in complexity, which required us to invest heavily in better observability. So we adopted things like eBPF to monitor our network calls and distributed tracing. So we really understood the call patterns and dependencies of our microservices.
Yeah, so just as Jay mentioned a term called hyperscale, right? So let's understand that term by looking at business in the form of a S curve. The S shape represents growth over time, starting out slowly, picking up speed during rapid growth, and then tapering off. Hypergrowth occurs when the organization's compounded annual growth rate exceeds 40%, which is much more than normal growth, and hypergrowth businesses are the envy of all venture capitalists. However, the sad truth is that most companies that experience hypergrowth fail because their management teams are not set up to achieve scalability and handle some of the challenges that come along the way. So for companies to maintain a sustained hypergrowth phase over several years requires these companies to be constantly innovating, launching new services rapidly for their customers and improving customer experience. They also want to make their application or platform highly available and performant so as to prevent any kind of revenue loss. These companies see a tremendous increase in the use of application or platform, which requires them to have high level of scaling, which is what we call hyperscale. Such hyperscale brings with it its own set of challenges, and DoorDash has been one of those companies who has successfully navigated these challenges, which we'll uncover in this session. So, what did hyperscale look like for DoorDash, Jay?
Yeah, yeah, awesome. Just to pick a few numbers that can provide a bit of insight into the scale and complexity at which we operate. Today, we see an average of 150,000 requests at the front door. A single HTTP request can often fan out into thousands of requests internally. And today, our engineering team manages a little over 1,000 services across 20 Kubernetes clusters. And one of the main takeaways that I can share from operating at this scale and seeing our own architecture evolve over time is that no matter how well something's architected, something is failure is always within the realm of possibilities. It's literally a universal truth with anything involving humans. So you should build with this in mind. We dug in a bit further at DoorDash and we were able to bucket failures into three major types. Testing is the first worth calling out. This is where a problem isn't caught in early in the release process. To avoid these types of failures, we invested heavily in things like unit testing, integration testing, load testing, performing progressive deployments to catch problems early before they impacted our users. The second type is around blast radius, where there's a single point of failure in your system, either due to some sort of shared state or strong coupling. A good example of something like this may be your secret store, where many services rely on it to retrieve secrets. And if it's down, then obviously all your services are impacted. Or a T0 service, where it becomes, if it's unavailable, it results in upstream cascading failures. To mitigate these types of failures, we tried to limit the impact of a given change through domain isolation and putting guardrails in place like load shedding and circuit breaking to minimize the impact. And then the last failure type is due to complexity. Wood's theorem, put simply, is that if a system can get too complex for a single agent's model to be accurate, meaning that it makes making a mistake much more easier and making the system and overall harder to debug. And I'm kind of curious, what types of failures have you experienced?
Yeah, rightly said. So, when you hit that hypergrowth phase, the scale expected of your application reaches new heights. So, when demand increases for the app, all the underlying components have to be coordinated for scale, and your app will start experiencing superlinear scaling factors such as cross node lock coordination. Another challenge is that of deployment complexity. When you want to add new features or capabilities to your application, oftentimes we need to deploy multiple microservices in parallel, and problems of bad code deployment and unintended CI/CD config are not uncommon. This can potentially bring your application down, impacting all your customers. Now, at hyperscale, even your network is being stress tested. This can introduce significant latency and timeouts if the network is not properly provisioned and configured. And this can impact your online workflows, resulting in poor customer experience while accessing the application. Your services might be relying on cloud resources with regional limits or account limits, which can quickly get exceeded. And it's important to think ahead and plan for these limits. For example, the number of clusters in Aurora DB in a particular region is 40, and some of these are soft limits, so you can adjust them ahead of time. But then there are some which are hard limits. Think about EC2 instance network bandwidth, for example. So in essence, the nonlinear scaling of microservices allows your application or takes your application closer to hidden contention points. This results in what we call cascading failures or timeouts, which are harder to test. This results in outages or downtime impacting all your customers, and from that standpoint, it represents a larger blast radius. And if you remember, some of the key goals of hypergrowth, such as innovation, improving customer experience, preventing revenue loss, all of that can take a big hit. And this is not to say that microservices in complex environments is a bad idea, but it is so hard to get it perfect then that things can quickly get worse.
At DoorDash, we considered all the previously mentioned challenges that both Anon and I shared, and we've accepted that failure was inevitable. In fact, we use this as a major design principle for how we're thinking about our next phase of architecture moving forward, eventually converging on cell based architecture, which we codenamed internally Project Supercell. To give you a little bit of background, in 2020, a single deployment of DoorDash, its services, storage, everything, served all traffic for all markets out of a single VPC and a single account. When that single deployment failed, it meant the entire DoorDash business was impacted. Project Supercell sought out to add incremental, multiple isolated deployments of our business to contain the blast radius of any potential failure. And we had a few main requirements. These main requirements were that we needed failure isolation from a variety of failure scenarios, whether they were caused by a user change, a service failure, or failure of a managed cloud service. We also need to ensure that there was no overhead for our developers so they could continue to develop as usual without any additional friction. And then we need to be able to ensure that we supported our existing microservice architecture along with the new supercell deployment, which meant that we needed to ensure that services were routable regardless of where they were running. Now, let me pass it back to Anon to tell you a bit more about cell based architecture for those who might be less familiar.
Thanks, Jay. And so before we dive into Project Supercell, let's understand this architecture and how it helps in addressing some of the challenges of hypergrowth environments. So this architecture is based on the premise that massive scale requires parallelization, and this requires components to be isolated from each other. These islands of isolation are called cells. Each cell is a complete independent instance of your application, and has a fixed maximum size. Now, your application can be comprised of EC2 instances with auto scaling groups, or multiple containers, or Kubernetes clusters. You essentially run separate copies of each of these in each cell, and then your environment can grow by running, by adding more cells to support additional users or traffic. And again, failure in one cell does not impact the others. Now, do not confuse this with things like spreading across availability zones or regions, which provides physical isolation at the infrastructure level. Whereas this isolation is at an application level, where the application, is at a logical level, where the application environments itself are separated from one another. And then finally, you build a thin layer on top to route traffic to these cells. We call it the thinnest possible layer, just to remind everyone that this should not be some complex logic, but an efficient routing mechanism. So let's look at some of the benefits of this architecture. Let's say there is a catastrophic failure in one of the cells. The others are unaffected by it, and so only customers served by that cell are impacted. So in that sense, they represent bulkhead units that provide containment for common failure scenarios, and which means lower blast radius. Now, not only is the blast radius reduced, so is the probability of an outage. Since these cells have a consistent capped size, which is regularly tested and operated, you should see a higher mean time between failures. These cells are also easier to recover because they limit the number of hosts that need to be touched and analyzed for problem diagnosis and for emergency code deployment and configuration. So you should see a lower mean time to recover. Now, the capped size also allows for well understood and testable maximum scale behavior. So provides for better testability. You can run your canary tests in one of the cells, or tests such as chaos monkey, and without impact to other cells. Now, let's say you have version 1 of your application deployed in all of the cells, and you are coming up with new features in version 2. You can deploy it in one of the cells, make sure it works, and then roll it out to the others. Now, let's say if the deployment goes wrong, you can always roll it back without having an impact to the other cells. So this reduces the blast radius from the standpoint of problematic deployments as well. And finally, as a side effect, it allows for a scale out rather than a scale up and provides for higher scalability. Now let's look at some of the concepts of this architecture. One is, of course, the placement strategy, which decides how customers or workloads are mapped to cells. Router is the component which handles the customer traffic or request and directs it to the right cell. And then this architecture, it benefits from maintaining a maximum size of a cell, and you want to decide on the cell size based on predetermined scale of traffic. Let's look at each of these in little more detail. So the placement algorithm is a foundational component. It keeps track of cells, their configuration, and how different customers or workloads are mapped to them. And it requires some, you could use, for example, market segments or customer accounts as a mapping criteria. And it requires some thinking about, how you want to partition your data or traffic based on the business context. And it could be different for, let's say, B2C applications versus B2B applications. But the key thing to keep in mind is that you want to partition based on the grain of the service that allows for complete isolation. Now, your placement strategy will also have a bearing on the growth. So as you add new cells to your environment, it will need to keep track of that. Now, when customers access the platform, they should be able to conveniently, route it to the correct cell endpoint. This function is handled by the router. Now, this could be an out-of-band discovery mechanism which allows the clients to figure out which cell endpoint they should connect to. For example, you can achieve this using Amazon Route 53, a highly available and scalable DNS service, which provides several important features for the routing layer, such as distinct domain names per cell, routing policies, health checks based on which you can redirect to a failover cell, and so on. Or the router could be a proxy service like Amazon API Gateway, which frontends the request and then directs it to the appropriate backend cells. In this case, the parameters in the request itself can be used to determine the routing path, and clients will be completely ignorant of the backend cell design. Routers should introduce minimal latency, ideally in microseconds, and should not have too much complexity. And again, it is a component which is an important one from an overall availability perspective, and should not itself become a single point of failure. Coming to sizing, it's an important consideration to determine based on your routing criteria. So smaller cells means smaller blast radius. It's just easier to test, easier to diagnose and resolve issues because there are fewer log entries to query, fewer hosts to log into, and so on, and just makes it easier to operate at an individual cell level. On the other hand, if you have few large cells, it provides for better capacity utilization. You can accommodate big customers, as in whales, into those large cells, and then just makes it easier to operate at a system level. Now, here is an example application which is spread across multiple availability zones to take advantage of that HA architecture. And this is how a cell-based architecture will look like. Each cell providing the full capabilities of the application, and they are completely isolated from one another. And there is no inter-cell communication. So the router is the only component that knows about the underlying partitioning. Now, there are several ways you can partition. If you want to partition or segment based on geographical location, you can use geo-based cells. Or if you want to do it based on customer accounts, you can use some kind of a hashing algorithm to map those accounts to specific cells for efficient allocation and utilization. You still want to ensure high availability within a given cell. So spreading your application and application components within a cell across availability zones is highly recommended. As you all know, Amazon Virtual Private Cloud, or VPC for short, spans across multiple availability zones and can serve as your cell boundary. It doesn't have to be a single VPC though. Your cell can comprise of multiple VPCs, and this might be determined based on your VPC sizing, based on the application needs or the isolation that is required between different teams and their application components. So you want to separate them out in different VPCs, or just separating out business logic components from data layer components and so on. VPC peering provides the low latency networking connection between VPCs and allows to route traffic between them as if they are on the same network, and it provides a really good network performance to support this architecture. Now, one of the best practices is to have separate AWS accounts for your router as well as for each cell. AWS accounts provides a natural isolation boundary, so action in one AWS account does not impact the others. It also reduces the risk of hard service quota limits, which are mostly at the account level. You can use AWS organizations to create that multi-account environment to support this architecture. And then there are also some services like AWS Control Tower, which makes it easy for you to set up and govern a secure multi-account AWS environment called the landing zone. and it brings in ongoing account management and governance best practices that we have learned over the years by working with customers as they move to the cloud. So now you can have multiple cells within a given region and have an ability to interconnect them using AWS Transit Gateway. AWS Transit Gateway is a highly scalable and a highly available centralized routing hub and simplifies your network topology. And it need not be for your online customer workflows, but can provide an out of band path for your DevOps teams to get into these cells for troubleshooting, for deployment, and so on. Using services like AWS Direct Connect, site to site VPN allows you to connect from your corporate network or your on premises data centers into this architecture. Remote workforce can use AWS Client VPN as well to connect to this architecture. Now, this transit gateway hub and spoke model can enable connectivity for other offline use cases. Let's say you have a data platform environment which needs to connect to these cells to capture all the data or query all the data for building use cases such as for analytics and machine learning and so on. Now you can take it to the next level where you are building cells across multiple regions. This could be for reasons such as survey having cells closer to those markets where for obvious benefits of performance and latency improvements, or purely for scaling out to adjacent regions for higher scalability, or to get past regional limits on cloud resources. It could also be for regulatory reasons such as data locality while serving certain markets. But keep in mind that this is not to represent an active environment across regions, as this architecture again relies on complete isolation between cells with no dependency between them. And there are some good global AWS services that can aid in this design. We talked about Amazon Route 53, which is our DNS service with a variety of routing policies, which allow you to route requests to a cell's DNS endpoint across regions. There's Amazon CloudFront, which is our content delivery network, which allows you to securely deliver content with low latency and high transfer speeds using Amazon Global Backbone. It allows you to serve content from multiple origins using a feature called behaviors, which can determine the routing path. And then there are functionalities like CloudFront functions, Lambda at edge, which can be used to write custom routing logic to map to the right cell endpoint. Now, the main goal of a CloudFront CDN is to cache content and serve it from edge locations. But let's say if your application requires users traffic to flow all the way to the backend application, but still get good latency performance, you can use AWS Global Accelerator. Global Accelerator is a networking service which improves the performance of your users' traffic by up to 60% by using the global network infrastructure. When internet is congested, it can optimize the path your users traffic takes to your backend application using anycast technology, and it keeps the packet loss, jitter, and latency consistently low. It has a feature called custom routing accelerators, which can again be used to write your routing logic and map your users to specific endpoints or of cells behind the global accelerator. Now, there could be scenarios where, let's say, a cell goes down and you want to redirect to another cell to serve traffic from that other cell. And this is where Route 53 application recovery controller can help. So, application recovery controller service helps you to make sure that your applications and components within a cell are ready to receive traffic, and then helps manage and coordinate failover using readiness checks and routing control features. So, essentially, you will be able to make sure that the new cell is ready to receive traffic and then shift traffic to that cell using this service. So as you can see here, there are different ways you can design and implement this architecture. You may also consider some homegrown implementations or third-party solutions to come up with this design. AWS provides a good set of tools for you to think about this design and implement this architecture. So now that we have looked at this architecture, let's look at how DoorDash has implemented this to support the hyperscale growth.
Uh, Thanks, Anand. I think a good starting place would be to first look at our global cell. It's worth calling out that this is basically our existing microservice architecture. We just renamed it the global cell, and services yet to be migrated to Supercell live there by default. It includes our monolith, which is running in Kubernetes these days, MainDB, various other domain-specific databases, as well as a handful of Kubernetes clusters that house our global services. All of this is deployed across multiple AZs, and we introduced a service and internal router to support our various routing needs as part of Project Supercell. This is all deployed to our main account where everything had been previously deployed since literally the beginning of DoorDash. Here's a look at one of our cells that's part of Supercell. It's pretty straightforward. It's basically some storage, some compute. This time we have a single router, our service router, which includes console for service registration discovery, as well as a handful of Kubernetes clusters, some domain-specific databases that are still shared across our cells today. And then, of course, we use transit gateway and peering for different use cases, which we'll get in a little later. So looking at the VPC networking and connectivity, for user access, we use Transit Gateway alongside the AWS Client VPN for accessing various internal resources. For service-to-service networking, we use peers to avoid any additional hops that might introduce unnecessary latency. We ensure that there's no network path between our cells, and though it may appear that routing between them might be possible because there's a transit gateway attachment, we make sure that all the routing tables are configured as such where we restrict any cell-to-cell traffic. On the topic of cell size and allocation, something that Anand mentioned, we began thinking about how we were going to break up our cells in terms of what gets routed where, and naturally for us, markets were a perfect fit for this. Our business is made up of multiple markets that are distributed across multiple geographies, and determining them is pretty straightforward for the most part, because we can use something like the delivery address to determine a user's market in which they preside. The market is returned to our various clients using BFFs, which we will get into on a subsequent slide, but I want to call out a little more about why markets. As one might guess, some markets are smaller than others in terms of order volume. Additionally, we see order volume surge for different markets at different times of the day. Considering these properties, we distribute the order load of the markets evenly across 3 of our 4 cells, and we keep our first cell intentionally smaller to ensure deploying to it always has an undersized impact. Having different peak times actually lends itself as a useful property to perform progressive rollouts to markets during different times of low volume. As I mentioned on the last slide, we rely heavily on BFFs to return our user's market ID. BFF, for those who are less familiar, stands for backend for front end. It's basically a proxy between our clients, such as the mobile app is a good example, and a backend service. So maybe like the consumer service. A typical flow looks like this. The client calls the BFF first. For instance, the mobile client calls the mobile BFF. Then the BFF calls the consumer service internally. The backend service uses something like the consumer's home address to determine which market they reside in. And then it returns the market along in the response to the BFF and subsequently onto the client that sets a cookie with that market ID. Now, given everything that I've shared thus far, let's take a look at what a typical lifecycle of a request might look like. First, when the client makes a request, it always goes to our CDN. And it's likely at this point that first request doesn't have any information like the market that the request belongs to. The CDN worker then round robins a request to one of the 4 service routers residing in our cells. If the request is a cell service, we'll get into other types of requests a little later. From the service router, from within the cell, the request continues on to the BFF layer, which interacts with the appropriate backend service to determine the market that the user belongs to. The market ID cookie is then set. Diving into this in a bit more detail, again, the request is made to our CDN. Our CDN is used for various reasons, DDoS, URL rewrites, load balancing, but I think the important one worth calling out here is that is the worker functions that act as middleware for handling which service router to route a request to based on the market ID cookie. So first, we check for that market ID cookie and check if it exists. If the request is missing, the cookie again gets round robined to one of our 4 cells. So in this case, maybe the request goes on to cell 2. And as I mentioned, the request then goes on to the service router, which is an ALB, where the underlying instances are running both Envoy and Console. Console in this case is actually to support service discovery, is actually for service discovery purposes, and it's hosted using a specific domain. that Envoy uses for its lookups, not pictured. And important for how this whole thing works is that there's a catalog sync running in each Kubernetes cluster in the cells that registers services to console when a service comes up in the cluster, making it available for service discovery. Envoy then, of course, uses service discovery, like that service discovery domain, like I mentioned, for static vhost entries for each cluster to resolve a given workload into one of those Kubernetes clusters. The actual Envoy config itself is pulled down periodically via a runtime daemon on the node from S3. Let's say the request in this case is trying to resolve the consumer BFF. Well, it uses the console DNS server to first resolve the request, and we return IP for that service. The whole returning the IP thing is only really possible because we operate a flat network by leveraging the AWS VPC CNI in Kubernetes, which basically means that every workload in our cluster gets a resolvable IP address. Now that we have an actual IP, the request then flows on to the consumer BFF, and that BFF then interacts with some backend service to determine the user's market ID, usually using something like home address, like I mentioned earlier. So then on subsequent request, we now have a market ID cookie when the request arrives at the CDN. And the CDN then takes that request and then routes it to this specific service router based on that market ID. Then the service is routed to a workload running in the Kubernetes clusters in the appropriate cell. And then, of course, looking at this in a bit more detail, the request arrives at the CDN. There, the worker function performs a cell lookup based on the market ID. Once we know the appropriate cell, the worker then knows which service router to send the request to. So this time in our example, let's say that our market ID cookie is set to 123. Requests for market 123 are sent to the service router in cell 1. And that's basically it. In some cases, there may be requests that are made to a service that has yet to be onboarded to Supercell, and it might still live in our global cells. For these, they're configured as global services in our CDN, and the requests are sent to the service router running in our global cell. From there, the service router then routes the request onto one of the Kubernetes clusters running in that global cell. Let's say that we're trying to resolve, a hypothetical global service called the food service. Based on DNS records configured within our CDN, the request is then sent to the global cell. It then goes to the service router running in that global cell, which, like the cell service router, is running as an ALB with some instances running console and Envoy, basically identical to our cell service router, to resolve global services and the global Kubernetes clusters. Of course, there's still one more scenario that's worth calling out. That's when requests need to be routed to our monolith. Unfortunately, there are cases where this is still happening. So the request first goes to our CDN and then on to the service router as usual in our global cell. The big difference here is that the service router in this case is configured to send any request to the monolith onto what's called an internal router. From an internal router, there is a configuration where the requests to the monolith are sent to a service type load balancer managed in Kubernetes, where our monolith is running. And here's a bit more detail, or rather a look at that routing. The important thing here to call out is that there is an entry in the global service router where it knows to send certain requests to the internal router. And then the internal router has some endpoints that are configured for the monolith that sends those requests to the service type load balancer for our monolith. The internal router is also used for properly forwarding requests onto the appropriate service router. So let's imagine you have a global service that needs to resolve a cell service. It first sends that request to the internal router, and the internal router basically forwards it along to the appropriate service router. In that example, it would send it on to the cell service router and the Supercell VPC. As we've seen thus far, we operate a global service cell and 4 supercells. So I know it's a bit confusing. So I wanted to share a bit about the considerations that are made when we're considering onboarding a service to supercell and which sort of stay in the global cell. The first thing that's important to understand are our services dependencies. So basically, what are our services calling and where are they running? The reason this is important is because we need to make sure that the network paths are in place for our services to be able to communicate, and that traffic can go from one VPC to another. So there's no disruption when the service gets migrated. The other thing that's important to understand is the latency impact of moving your service. The last thing that you want is moving a service, incurring a bunch of unnecessary latency that impacts the overall performance of your system, because most of its dependencies are not running alongside it. So, like, let's imagine I move a service to supercell, but most of the things that calls are running in the global cells, or maybe it's sort of all over the place. It's going to result in a bunch of unnecessary traffic hops between the global and supercell cells. And also there's obvious cost implications to this traffic as well. Some things that are sort of out of scope for supercell are things like singletons, where you don't want a bunch of them. Imagine workloads that aren't idempotent, or schedulers. They're just not great candidates because you're not going to run multiple copies of them. So they'll always likely live in a single cell. And for us, that's the global cell. Lastly, tier is the absolute most important thing when we considered onboarding for services to Supercell. We focused on tier 0 services, as they are the services that are required for our business to operate. And really what we cared most about with Project Supercell is ensuring the business operated, and we had the ability to run multiple copies of the entire business. I want to chat a little bit about deployments and what a typical deployment looks like. So here's a quick look at that. So if it's in Supercell, remember again that the first cell is intentionally smaller. So when we do a deployment, there's a much smaller impact when we're deploying to cell 01. First, we do a canary deployment to cell 01. We follow that up with a canary analysis, make sure everything looks good. If it does look good, we proceed on to a blue-green cell deploy into that cell, where we basically run the old and the new version of a service in that cell and gradually shift traffic over from the old to the new while maintaining the old for potential quick rollbacks if necessary. If all looks good, we then continue on to the remaining cells, and that's pretty much it. And honestly, this is the exact same strategy for our global service cell. Finally, I want to wrap things up and I want to talk about resilience. So let's imagine a cell faces some sort of hypothetical failure. It could be a runtime change. Maybe it's some sort of bad change to a secret. Maybe a deploy just goes wrong, resulting in cascading failures. The first thing to point out is that the impact is isolated to that single cell. Only markets that reside in that cell are impacted. The other 3 cells are operating completely as expected with no issues. Once the outage occurs, the first thing that we do is we shift traffic over to the other 3 cells. Basically, we remap all the markets to those other 3 cells, and we remove that particular cell from a round robin pool to ensure that no requests are being sent to it. Once we're ensured that traffic is completely steered over from the bad cell, the team then determines and resolves the issue within that cell. And finally, after everything is fixed, the cell is re-enabled with the markets mapped back to the cell, as well as it being added back to the round robin pool. All of these operations are driven by a CLI that we have internally, and it's called Healer. As I mentioned much earlier in this talk, the shared storage thing is kind of an important thing, or rather our shared domain-specific database is a very important point. Some of you might wonder why we're able to get away with this steering of traffic between one cell and the other 3 healthy cells in the previous example. And this is primarily because Supercell is a multi-phase project for us. The focus for phase 1 was all about isolated compute, getting our foundational networking routing in place while still maintaining that shared storage. For us, this means that software deployments can now be phased across multiple cells. And with the shared storage model, we're able to fail over markets to any given cell if necessary. The shared storage model will obviously be the next thing to go in phase 2, as we don't want that to become our single point of failure. So if you had something go wrong with one of those shared databases, it would impact all of the cells today. So in phase 2, the focus is on data sharding, where each cell has a subset of multiple markets data for each domain-specific database. So we still get the benefits of having multiple cells that can serve a given market. Though it is worth calling out that phase 1 alone offered a lot of benefit in tackling the compute problem first, and deprecating our monolith was important to us. Plus, sharding stateful systems is expensive, and so we kept that in mind too when we were thinking about phase 1. Our last phase 3 for us, will be literally just getting this entire setup deployed to one more region to avoid the very unlikely regional outage. One thing I can say, though, from the overall experience with this new architecture is that it's been great. It's the ability to re-steer traffic to a healthy cell feels almost like a superpower. Plus, engineers have this improved confidence iterating on changes and shipping new features, knowing that the impact of their change is minimal, and that if necessary, we could steer traffic, disable entire cell, and then steer traffic to the other three. And we've also seen this drastic decrease in MTTR, as well as an increase in dev velocity across the board since the beginning of Supercell. Though overall things have been great, it hasn't been without its own handful of challenges here and there. Though most of these came from the complexity that we accepted in the short term to support our monolith, our global, and our supercell deployment. The first notable challenge was around onboarding. We honestly expected folks to onboard much quicker than they did, but various service dependencies made this more challenging than expected. Initially, we also saw higher than expected latency across our cell VPC to our global VPC. So we invested in tooling and observability to identify bottlenecks in our network paths. We moved all of these network paths to peers, which greatly improved our latency. Lastly, the router has somewhat become this really the single point of failure and fragile to the overall system. So config changes need to be rolled out slowly and properly validated. For us, the journey isn't quite over. We're still working on various initiatives around Supercell, a lot of which I've already sort of shared at this point. As I mentioned, these include data isolation per cell, simplifying our overall routing setup. And there's actually this opportunity to remove a internal router once service mesh is fully adopted. And then investing in tooling to improve the overall onboarding experience, or rather, minimize the number of PRs that engineers are having to open across a bunch of repos to onboard their service. So the way cloud's tackling this is through SAN abstractions for folks onboarding to Supercell, where they only have to go to one place to get their service onboarded. We're also working on ensuring that multiple markets can continue to be served by multiple cells. And then finally, I keep saying it, but we want to deploy this whole thing to multiple regions. And that's Supercell in its brief entirety. I'll pass it back to Anand for some parting thoughts.
Sure. Thanks a lot, Jay, for sharing this journey with us. And so, based on this journey, I mean, some of the best practices or considerations that come to mind, and I wanted to share with you. So, first of all, as we discussed, cell sizing, right? So, more smaller cells means smaller blast radius. So, it's always good to approach the design from that angle. It's faster to diagnose, resolve issues with smaller cells, easier to test, and you can leave more room to grow if needed, right? The other thing is ensuring that you have a good health check for each cell, so building cell level metrics like canaries metrics, alarms, dashboards at an individual cell level, so that you understand the health of each cell is pretty important. Now, of course, from that standpoint, the other consideration is it does increase a little bit of the operational complexity. And then, of course, you are going to deploy to these cells in a staggered manner, so the deployment duration might also increase. So please take that into account in terms of the operational complexity, make it part of your operational playbook, and so on. Now, one thing you might have realized from the cell router perspective, it can become a single point of failure. So don't think of it as a single entity trying to distribute traffic to cells, but rather take advantage of some highly available, highly redundant services or managed services to implement that router. Now, coming to the last point, the cell migration. And cell migration essentially means moving your workloads or customer traffic to another cell. And this is a complex problem because it does involve data migration. And it's okay to do that, especially for scenarios like failure recovery, where your one cell is down and you want to redirect traffic to another cell. But then there could be other scenarios where you can think about cell migration. Let's say there are one customer or a few customers occupying the cell, which is like overloading the cell, and you want to move them elsewhere, or you want to do some kind of optimization in your cell design, so you want to move certain data partitions to another cell. So don't boil the ocean on this one, as it's not going to be a problem for on day one. And since you are adopting the cell based architecture, and you're still going with the strategy of ensuring the right cell size and so on. The problem of one customer or few customers overloading your cells is not too high. All right, so with that, I want to come to the final parting thought. And like our CTO Werner Vogels mentioned, everything fails all the time, and you can't control that failure, but you can definitely control the impact. So as we discussed today, hypergrowth companies face challenges of scale, deployment complexity, and resource limits. This makes it hard to deploy new features quickly while maintaining uptime, and has an impact to revenue and customer experience. The cell-based architectures that we saw today has some promising characteristics, and you can to enable the failure isolation and get the benefits of scale out. Also, it is not an alternative to microservices architecture, rather a way for you to approach your microservices with agility and confidence, while ensuring that impacts of failure are minimized. So given the concepts that we have learned today and some of the learnings from the DoorDash story, I strongly encourage you all to bring in that thought process and choose among the various services available to come up with this architecture for your environment. AWS provides a good set of tools and services to help you with this design, as we discussed. And here are some resources for you to look at on those similar topics. Starting with the cloud native architecture series, there is a good blog series that you can take advantage of. Reliability pillar of well architected provides good information on the resiliency focus, as well as the resilience hub has a lot of useful resources. And then one of the blog which talks about the fault isolation handling within our own AWS services and how it uses some of the cell-based architecture principles. All right. So with that, on the last topic, I want to point you all to some related sessions on similar topics which were part of AWS reInvent 2022. They should be available on our YouTube channel of AWS. I strongly encourage you all to take a look at those. And with that, from both me and Jay, thank you for your time, and we welcome your feedback.
Thank you.
Thank you so much.